Okay, another application here, linear approximations and differentials. So if we have a function and we look at the tangent, you can see that if you're very, very close to that point of tangency, in this graph right here, x equals a, the tangent line is going to be really close to the true value of the function. So if you move just a little bit left or right, the tangent line is going to give you a very good approximation. And clearly, the further you get from x equals a, the worse that approximation becomes. But very, very close, that approximation is actually pretty good. And we call the equation of the tangent line the linearization. So to come up with the linearization of a function, let's start with y minus y1 equals m times x minus x1. We'll call our x value a, then y sub 1 is f of a, and our slope is f prime of a. So plugging those into our equation up above, and then solving for y, and we can just rename this function L of x for linearization of x. So this right here would give us essentially the tangent line for the original function f. And that linearization can be used to come up with approximations for points close to a. So this formula might look a little bit confusing as it's written. Just keep in mind all it really is the equation for the tangent line. So you don't really need to memorize this formula as it's written. Just know that if something asks for the linearization, you need to go through the process of finding the tangent. So I want to find the linearization, or the tangent line, of this function when x equals 0. We're going to use that to approximate the square root of 1.02. So let's take the derivative to find the slope, and we evaluate the derivative when x equals 0. The y value when x equals 0 is 1. We get that by plugging it back into the original equation. So here's our point slope form of the line. Plug everything in, solve for y, and we just give that a special name, L of x. So linearization of x is 1/2 x plus 1. If we want to approximate the square root of 1.02, that's f of 0.02, because 1 plus x, or 1 plus 0.02, gives us 1.02. So that function value is approximately equal to the linearization of 0.02. So plug that into our equation L of x, and we get 1.01 as our approximation for the square root of 1.02. And let's check, since we do have a calculator available to us, we can see what this square root actually should be. And if we find the difference in error there, we're off by 4.05 times 10 to the negative fifth, which is a very small amount. So you can see this approximation was pretty good. If we had tried to use this approximation for the square root of 20, it would not be very useful. We have to have values that are close to our original x value. Okay, now we're going to introduce something we call differentials. When we first started talking about derivatives, we looked at delta y over delta x, that change in y over change in x. And as the change in y and the change in x become very small, we called that dy dx. So we're going to think about dy as a very small change in y and dx as a very small change in x. In reality, they're infinitely small. They're just as small as you can possibly get. When we use these differentials, we're going to allow them to take on some actual value. And we'll see when we do that, it's going to give us an approximation rather than an exact value. So here's our function. Y minus y1, we can call that delta y. X minus x1 is delta x. M is f prime of x. And as delta y and delta x get really small, we can call those dy and dx. So let's say that we have dy equals f prime of x dx. Now, keep in mind that dy and dx are these infinitely small little pieces. As soon as I give it a value, if I say dx equals 0.1, this equation now becomes an approximation because I've given it a finite value. So let's say we have a circle of radius 10. If the circle increases by 0.1, how much will the area change? So here's an equation for area, pi r squared. If we take the differential, we get the derivative of a is dA, the derivative of pi r squared is 2 pi r dr, and our value for dr is going to be 10. So this is going to turn into an approximation once we give that thing an actual value. And simplify this down, the change in area is approximately 2 pi. Okay, if we compare this to the actual change, we can find the new area by increasing the radius to 10.1. The old area was when the radius was 10, and if we take the difference, we'll compute this as our difference between the two values, our approximation and the true value, over the actual value, and you can see our percent error is 0.5%.